together. Lori, on the way out, maybe see if people are still outside, kind of encourage them to come back in. Thank you very much. Okay. Well, welcome back. We continue the VCR seminar series, and our next speaker is Dr. Ed Storms, and he is retired from Los Alamos National Laboratories, now operates Kiva Labs LLC in Santa Fe and in Greenwich, Connecticut. And as many people probably know, he's the author of the book Low Energy Nuclear Reactions, which I believe was published 2 years ago, or? Oh, very good. Well, Dr. Storms, please.
Well, thank you, Dr. Duncan. Oops, I don't want to break it. The subject of cold fusion has gotten such bad press, both from respected scientists as well as from the press, that there's a considerable amount of skepticism about the reality of the subject. I would therefore like to assume the role of a skeptic. I think that would be better at it than most amateur skeptics because I've worked on the field for 20 years and probably know more about the flaws than anybody else. So as an honest skeptic, my first job would be to actually learn something about the subject, which is fairly rare in skepticism, I find, in this subject. You can go to the website www.lenr.org, and there you can find over 3,000 papers relevant to the field, many of them in full text. You can find reviews, summaries, commentaries, pictures of apparatus, and in fact, you can find anything that you ever wanted to know about cold fusion but were afraid to ask. Or if you forgive my self-promotion, you can buy my book and read it, in which I go into some detail about the field, both evaluating the information that's been published as well as some of the theories. Well, the first thing we need to do is show the contrast between hot fusion and cold fusion, because many skeptics are hung up on the characteristics of hot fusion and have not made the transition to cold fusion. The hot fusion is well known. It's been studied for well over 60 years. $22 billion has been spent on it. It is well accepted, well understood, and is considered the only way in which a fusion reaction can be made to occur. And it uses high translational energy to blast through the Coulomb barrier. This is a brute force technique. The characteristic reaction products are equal amounts of tritium and neutrons. So if you don't get that, you don't have tritium, or don't have fusion by the skeptic's point of view. It's initiated in a plasma or by ion bombardment, intense laser light, and a number of other techniques. Now, in contrast, cold fusion uses a process in condensed matter at modest temperatures to lower the effective Coulomb barrier. It's very similar to the effectiveness of a catalyst in lowering the activation barrier to chemical reactions, except now it has to do with a nuclear reaction. The characteristic reaction products are helium, occasional tritium, rare neutrons, transmutation products of various kinds, and low energy radiation. We'll go into some more detail about each one of those subsequently. It's initiated a number of different ways: by electrolysis, gas discharge, ambient gas, or sonic implantation, and we'll talk about some of those in more detail. Well, if I'm going to be an honest skeptic, I need to have a criteria to be used to apply to this field, and we'll use the four that are normally used in any aspect of science. The quantity, that is, how often is the basic phenomena been observed? And from a skeptic's point of view, how many are enough? 1, 100, 1,000 replications? What do you require to believe something? The quality, how far above the expected error or uncertainty is a signal. In other words, how good is good enough? 1 sigma, 10 sigma, 1,000,000 sigma? I mean, how good does it have to be before you accept something? Consistent patterns of behavior. That is, the various measurements show the same relationship to 2 or more variables. If people see the same relationship to several variables, it's unlikely that the errors in those variables have conspired to always produce that relationship. And so if you see this behavior in a number of different variables, it gives you more reason to believe that it's real. Furthermore, can the phenomena be initiated more than one method? In nature, you can normally make phenomena occur several different ways. And if you find that there's only one way of making something work, that makes it very difficult to believe. So we have to see how cold fusion stacks up against those criteria. Well, the first and most important discovery was the production of heat. This is important because it implies a reaction rate of about 10 to the 12th, 10 to the 14th events per second. That's a very high reaction rate. It is also the discovery that would have some kind of commercial application. So it's very important to know whether the heat's real or not. To measure heat, you need a calorimeter. And just to give you an example, I have shown here the calorimeter that Pons and Fleischmann used. At least 4 different other kinds of calorimeters have been used. And Mike McCubry will later show you a flow-type calorimeter and the results therefrom. Each of these calorimeters have different errors, they have different characteristics. All of them have shown the same effect. So it's been seen by a number of different techniques. Now, the cell is very simple. It's a cell containing D2O plus LiOD, in other words, D2O with a little lithium dissolved in it. The current is applied to it, which causes the D2O to decompose. The deuterium goes into the palladium cathode, which is located here. As it loads up, if you're lucky, it becomes active and produces a nuclear effect. You can measure the amount of energy that's being generated in this system very simply by measuring the temperature difference between the inside and the outside. And the outside, in this case, is a constant water bath. If the wall of the cell is a solid, so that this heat is being conducted by solid conduction, then it's the delta T times some constant. In the case of Pons and Fleischmann, they had a vacuum there, and so the loss was by radiation, and that meant that you have to use the difference between 10 to the 4th. The excess power is simply the difference between the input power and the produced power, and A and B are determined by applying electric power to a resistor located here. So it's a very simple system. Calorimetry is well known. It's been used for over 200 years. We're not using some really strange, weird technique to make these measurements. It's totally accepted and understood. That being the case, what's the skeptic's argument? Well, the skeptics agree that calorimetry is well understood and potentially accurate. Therefore, the claimed excess power must be caused by failure to use the method properly. This failure must be caused by incompetence that results in errors being ignored that only the skeptics can identify. Repeated replication by many people is required to make the skeptical explanation less plausible. I mean, that's one of the requirements in science. That's why that requirement is there. However, in this field, the skeptical explanations can never be made completely implausible because the neutrons are not produced in the expected amount. So right away, we are in serious trouble in the skeptic's mind. Well, let's look at what has been published in the literature with respect to heat. This is a histogram of 157 reports of excess power. Now, within each one of these studies, more than one sample turned on and produced excess power. This is just the best of the lot that's been plotted here. And so this is the number of studies giving this much power. Well, first of all, I want you to notice that large amounts of power have been produced, and this is from a few grams of palladium. So we're not talking about a small effect here. But it's fairly rare at that level. If we go back to lower powers, you'll see that there is a significant number of amounts of power that are quite substantial, 20, 30, 40 watts. This, again, is trivial to measure. But most samples produce a few watts. Well, why is this? It's because the nuclear active environment is very difficult to be produced. It happens really only if nature's in a good mood that day. We don't know how to do it on purpose. And so these experiments produce a large amount of that environment on the surface or in the material. But most measurements produce nothing whatsoever. I mean, there's been probably thousands of measurements that were totally dead. Well, obviously nature wasn't in a good mood for those people. The challenge is to find the nature of this environment. And that has been the challenge, really, to master cold fusion. Well, let's also examine who it is that's making these measurements. Here's a very abbreviated list of the institutions that have reported the previous measurements. And I want you to notice that not only do they exist in various countries, but they're not trivial organizations. I mean, these are major universities, major companies, major organizations that are not amateurs. They know what they're doing. These are people who have had careers in other subjects of science, have done very fine work. Their competence has never been questioned in that context. And then suddenly when they report something in cold fusion, they've all of a sudden can't be believed because they don't know what they're doing. That doesn't make any sense. Well, what are the possible errors, or plausible errors, I should say, that could result in these effects? And let's address three of them. The failure to measure the correct temperatures. Now, that's a problem in calorimetry if you try to measure the temperature within the electrolyte, as Pons and Fleischmann did. Because the heat's being generated there, you get temperature gradients, convection currents, and so you cannot get a good temperature that you need that represents the temperature of the interior wall, the average temperature. Pons and Fleischmann's work was analyzed by a number of people, and this was published. They came to the conclusion, although Pons and Fleischmann, their error could be somewhat larger than they estimated, it could not be large enough to negate their results. Now that work has been thoroughly done, thoroughly documented, and published. So I think the failure to measure temperatures has been put to rest. The failure to consider energy sources other than nuclear. Now you can imagine all kinds of possibilities, but this is a very simple chemical system. So there are very few possibilities available. John Bockris, in the first year of this work in 1989, published a thorough analysis, and this was also published in a peer-review journal. It did a very careful analysis of all the sources of energy that might reside within the cell. And he came to the conclusion that, yeah, you can probably justify a milliwatt or so, but you cannot justify the amount of power that people have been seeing. And finally, the failure to measure the correct input power. This issue was brought up by Dr. Garwin in the 60 Minutes program. Dr. Garwin is a member of the JASONs. He was a member of the ERAB panel that was organized early in the history of the Pons-Fleischmann effect to evaluate the reality of the claims. He has interviewed people since then. He's a respected, competent scientist who you would expect to be very cautious in his evaluation of his understanding of the field. But he made the statement that he felt that he didn't believe that cold fusion was real because of the failure to measure the correct input power. Well, let's address that issue then. First of all, various methods are used to initiate the effect, and they differ in the use of input power. So if input power is the problem, then it's a variety of errors, not just one. There's a variety of possible explanations because each one of them has to be explained because each one of them produces the same effect, even though we use different techniques. The gas loading requires no input power. If you have specially formulated, finely divided palladium and simply expose it to deuterium gas at modest pressure, it will generate helium, heat, and occasional tritium. There's no input power involved with that. That observation, therefore, needs to be explained and cannot be explained by the input power problem. Life after death. Life after death is a phenomena that Pons and Fleischmann observed and other people since then. It is fairly rare. And that is if you have a cell or a piece of palladium in an electrolytic cell that's making excess energy and you turn the power, the applied power, off, this energy will continue for some length of time. Essentially what's happening is that while it's being electrolyzed, deuterium is going into the surface, supplying the deuterium necessary for the reaction to occur. When you turn it off, the deuterium comes from the inside that's been absorbed by the interior and comes out through the surface. And as long as there's enough deuterium left to supply that deuterium to the surface where the action is occurring, you continue to get excess energy. Furthermore, the electrolytic method was analyzed by Dieter Britz, published in Electroanalytical Chemistry, a peer-reviewed journal in 1995, and he did a thorough evaluation of that problem, of that error, and found that it was not a source of error. And there are some electrolytic experiments that actually deny this explanation. And here's one. This is a study done by using electrolysis by energetics technology. You saw some of the work earlier that Professor Duncan showed. Here we have a plot of the input energy, and it's less than 1 watt. And this is the energy being generated by the reaction shown by the calorimeter. And this is going all the way up to 34 watts. There's no possible error in this input that could generate this if this was caused purely by input power error. It's simply impossible. So the experimental evidence does not support Dr. Garwin's assertion. Well, if you have a nuclear reaction, you expect to see nuclear products. People look very hard for the expected nuclear products. They look very hard for neutrons. Hundreds of efforts were made to look for neutrons. Very few of them succeeded. Neutrons are simply not produced as a direct result of heat production. They do not happen at the same time as heat production. It was only when people started making the very difficult measurement of helium and relating it to heat that the correct nuclear product was found. This is the helium per energy, and known from the reaction energies, all the data should fall on this line right here. This is the 23.8 MeV per helium atom. These two measurements are 2 of 6 studies, independent studies made in various places in the world that I'm comparing. And you'll notice the scatter is significant, but not out of line completely. And this other study, which was done using a Seebeck calorimeter, has much tighter variations, but is in basic agreement with the first study. Also, the helium measurement was the helium that came out of the cell. We know that some of the helium is retained by the palladium. And you'd expect about half of it to be retained by the palladium. And that's where these 2 data sets basically lie with respect to what you'd expect. So this is very consistent, and all of the studies show basically the same result. Helium and heat production are the two results that are connected. Well, let's look at the some of the other behaviors. When I said that the effect has to show a relationship to various variables, let's show a couple of these variables. Here is the excess energy, and this is the current density being applied to the cell. Everybody who makes such measurements and has an active cell sees the same result. There's a region where absolutely nothing happens, and you have to be above a critical current density before anything is seen. If you are very lucky and you have a lot of nuclear active environment on the surface, you get this effect. If you're somewhat less lucky, you get this effect. There's less there. And of course, if you're very unlucky, you get nothing at all. But everyone who's made these measurements and who has made excess energy and made such a relationship sees the same thing. The other variable is the average composition of the bulk sample. This is excess power against atomic ratio. And you'll notice below a value of 0.88 for this particular sample, you get no excess power. And that was one of the problems, of course, early on in the field. It is not easy to get palladium to take up this much deuterium. And most samples do not, and therefore have no hope of working. But once you can get above that, and people now know how to make palladium that in fact can get into these regions fairly reproducibly. And when that palladium is used, one sees this relationship. So once again, here's another variable that everyone who makes the right measurements sees the same relationship. Well, the summary of what's believed by many people in the cold fusion field. And I might add that there are skeptics in the cold fusion field about some of this too, so we're not just talking about everybody in total agreement, but this is what I would say I believe. Both protium and deuterons can be involved in nuclear reactions, apparently as clusters. So, of course, they produce different nuclear products, but both can be part of a nuclear reaction. The reactions include DD fusion, transmutation, and fission. The fission occurs when several deuterons or protons go into the nucleus of a heavier atom that happens to be in the environment, and then that atom is unstable and fissions into smaller products. The reactions can produce energy, helium, with these two being together, energetic particles, tritium, neutrons. If it produces the two together, the tritium is usually 1,000,000 times greater than the neutrons. Transmutation products, photon emission on different occasions. I mean, these all don't happen necessarily at the same time. And the photon emission is both X-rays and gamma. And radioactive products are seldom produced. Not never, but seldom. So this is a handicap to some degree because it'd be nice if it did produce some because we could then tell what was going on. But if this is ever used as a source of heat, this is a great gift. Whoops, I seem to... And nano-sized material. Oh, well, reactions require a special arrangement of atoms in the solid lattice or in a living organism called the nuclear active environment. And that's where these reactions occur. Nano-sized material is important, especially for the gas loading. And the reactions can be initiated using electrolysis, gas discharge, gas loading, or sonic methods. So what does a rational skeptic have to believe to remain rational? They have to believe that each of hundreds of studies contain errors that were overlooked. They must believe that a majority of the hundreds of people studying the various aspects of the phenomenon are incompetent only when they study cold fusion. And furthermore, they must believe that it's impossible for a new mechanism to exist that can lower the Coulomb barrier under any condition. Well, you hear very frequently a mantra, extraordinary claims require extraordinary evidence. I mean, this seems pretty obvious. I would suggest that a corollary to that is required. Extraordinary evidence should not be rejected just because it supports extraordinary claims. So I thank you very much, and I'm open to questions. I hope you have.
This is a little bit off topic, but there was a posting on the CMNS list a while back that said that almost all palladium that you can buy in the U.S. is recycled. It's been used in various applications. It's been worked in various ways. It's been contaminated differently. And that's what you get when you order palladium from ASAR or whatever. Do you think that makes a difference in forming the NAE?
Well, there's two kinds of palladium on the market. There's the recycled palladium, and there's the virgin palladium. And one can get either one. Early in the field, people measured the tritium content of palladium, and that was the issue. And they explored it from a number of different sources, both virgin and the recycled. And they found no tritium whatsoever. And you'd expect that because tritium is fairly rare, and it would not be legally wise to put contaminated tritium on the market, or contaminated palladium on the market. So that's simply not an issue.
Okay. And does anybody in the field worry about the neutrons flying around? I wasn't clear about how normally in normal cold fusion experiments you don't get neutrons, but the Spauer people, when they apply the electric or magnetic field, get neutrons. So is there an explanation for that?
Well, yeah, I have an explanation for it. I don't know if they would agree. I think that they're seeing an aspect of the hot fusion reaction that's being initiated within the particular environment of their cells, and that most other people, although they occasionally replicate that environment and see neutrons, I mean, that neutron production is not unique. It's rare, but it's not unique. But most of the time, and especially with the production of heat, there is no neutron emission to speak of.
So does it correlate to some extent with the formation of the craters?
Well, when you measure the neutron flux and compare it to tritium, the tritium is a million times bigger than the neutrons. So it's not a typical cold fusion reaction, but neutrons are the most unlikely nuclear product that people see.
Yes, I'm Peter Handel from St. Louis. Just wanted to call attention to slide number 13 that you have. It's a good thing they're numbered. It's quite instructive, and it's important for, number 13. One more. The next one. That's the one, yeah. You see these straight lines. They show that the excess power is proportional with the current density. Not always do you have this clear result, simply because the heat development is dependent on the concentration of deuterium that you have arrived at already in your palladium. And together with Ahlefeld, we studied this back in the 60s. But I just want to mention that this shows that we have something that is explained through my thermoelectrochemical effect, has some similarity with the Peltier effect. The two different lines correspond to two different ways of connecting the electrodes, palladium and platinum, for instance, to the wires that come out of the calorimeter, or having the palladium and platinum rods themselves come out from the calorimeter. And so and these quantities here are measured, in fact, in calories per coulomb. And that's what we need to remember, because my talk is going to make a reference to this. We met, I met Professor Storms also in the vicinity of Los Alamos, in the mountains even, but of course we met at the various fusion conferences. And I highly value his contribution, and particularly this systematic presentation. And I'm one of the people who certainly believe that we will be successful with cold fusion, non-muon cold fusion. Thank you. And see in my talk what the origin of the true origin of all the excess heat that is right now accessible to our experimentally limited means. It's like working with optical tweezers rather than with a pair of mechanical tweezers.
Thank you very much, Dr. Storms. And I should add, too, Dr. Handel will be our last speaker in the session today, so we'll hear more about his work at that point in time. It's a great pleasure to welcome, sorry, I got a little bit turned around, but it's quite a pleasure to welcome Dr. Michael McCoubre, who's here today. He has been doing work for quite some time at this SRI Institute in California, and will speak on his work here. Thank you.
Well, thanks very much for inviting me. I probably need somebody who is more PC than I am to dig up my slide here. I'm sorry, I'm a Macintosh man. When I see a PC, I immediately panic.